Okay, welcome to class meeting 20 of EECE574, the graduate level probability and random processes. Quiz 2 will be taken next Tuesday during the class meeting. I haven't yet made up the problem set, so I'm not sure whether it will take around 30 minutes or a full 1 hour, 15 minutes. But anyway, fully prepared for the exam. It covers up to today's class meeting. Handouts are available from the course web page. Lecture videos are available. Homework, one more homework will be assigned, and please check the PLMS. There are some, not corrections, but clarifications, but I will talk about it after I say that I shuffled the order of some part of Populist chapter 9.1 and Populist 7. Last time, after I finished it, correlation functions and measurement of correlation functions, I moved to sequences of random variables. But today, I will quickly talk about these topics because they are related with correlation functions, and we'll go back to chapter 7. Here goes the review. Last time, we reviewed the definitions of correlation and covariance functions. And we also consider the problem of kind of estimating correlation functions of a random process. And there we assumed ergodicity. Otherwise, there is no way to get the ensemble average estimate from time average. So we assumed ergodicity in some sense. And that was actually all. And then we moved to chapter 7 of Populist, where I started with the kind of strange equivalent definition of the equality of two real numbers or two complex numbers. And we started from our friendly x equals y, and I claimed that this is equivalent to the statement that for all epsilon positive, it's like a magic spell in Alibaba and 40 Thieves, like Open Sesame. For every epsilon positive, you always start like that for the convergence of a sequence of real numbers or convergence of sequence of anything. And also when you when you talk about continuity of a function. For example, a function f of x is continuous at x equals x0, then what's the definition? For every epsilon positive, there exists the delta positive such that blah, blah, blah. So it's like for every epsilon positive always appears everywhere whenever you talk about the limit of something. Got it? So for every epsilon positive, absolute value of x minus y. If x and y are complex numbers, it's a modulus, but usually we say absolute value is less than or equal to epsilon. When you take here, strict positivity, actually, it doesn't matter whether you take less than or equal to or less than. But in many cases, putting equality is easier because sometimes you want to find, later you will see, some capital N over epsilon. In that case, putting equality here is much convenient. So this is a better way, but this is perfectly okay. However, if you put equality here, then it's okay now, for now, when we talk about equality of two real numbers. See that? For every epsilon non-negative, right? X minus epsilon is less than or equal to epsilon. In that case, suppose x equals y and you choose epsilon equals 0. No problem, right? X equals y, and you choose some epsilon, very small positive, still okay. However, here, this statement is totally wrong. See that? You want to show that x equals y, the statement, is equivalent to this statement. However, if you choose epsilon equals 0, right? Then x minus y is 0, but 0 cannot be less than 0. So never use equality here and no equality. So this is not a good combination. It's a bad combination. And you will also see that this is also bad when we talk about the convergence of something or continuity of something. So you always had better to use the previous two. Got it? Sometimes it's convenient, sometimes it's convenient. Got it? Anyway, you can easily prove using the proof by contraposition or proof by contradiction. In that case, in here, P is equivalent to Q, is that P implies Q and Q implies P. And you know that Q implies P has contraposition, which is not P implies not Q. So P is equivalent to Q is same statement as P implies Q and not P implies not Q. And if you prove in this way, you may say that I've proved something by contraposition, okay? Or I use the proof by contrapositive, something like that. But contradiction is a little bit different because we change these two as P and not Q is false, something like that. But actually they are, according to the truth table, they are the same, right? Anyway, so equality of two real numbers can be strangely restated using epsilon, positive. Got it? That's the point here. And for the approximate equality, I mentioned that bounding is also very good approach. And I told you the story of my advisor, who was a young 27 probably year-old PhD, getting a assistant professorship at top 10 university by deriving upper and lower bound of the direct sequence spread spectrum multiple access communication speed error probability. At that time, it was, many people believed it has very exponential complexity to obtain that, but he used an interesting trick to reduce the complexity to polynomial and derive the upper and lower bounds. And that upper and lower bounds could be tightened arbitrarily if you have more and more computing power, something like that. Anyway, so bounding is very important. You use inequality of given some quantity, you have lower bound and upper bound, and you subtract these two and say that this is the upper and lower bounds are close enough. Done, right? But there is another way, and this is more popular because sometimes bounding is much difficult than showing the convergence of a limit, convergence of a sequence of something. So here, you want to show X is approximately equal to Y. There is no sequence given. However, you construct a sequence, Xn, okay? And that Xn is a sequence. And you show that Xn converges to Y. Then you may claim that Xn is approximately equal to Y for sufficiently large n. Then we need the definition of a convergence of a sequence of real numbers. So here goes the definition. For every epsilon positive, it's like a spell, as I told you. For every epsilon positive, you can find, there exists, means you can find n of epsilon. So your choice of n depends on this value epsilon positive. And this n is a natural number because we assume that the index is a natural number such that, and as you see, there are two choices, whether you put equality or inequality. And as I told you, it doesn't matter here. Okay? However, it's convenient to put equality to really find n of epsilon, sometimes, not always. But anyway, so you choose, you can, given any epsilon positive, you can find, or you can choose n of epsilon, a natural number such that the difference between x and x, the limit and x, or you may say that x and y here. Okay, let me use y because it makes more sense here. Yeah. Okay, so the difference between x sub n and y is less than or equal to epsilon for n greater than capital N of epsilon. If we draw a graph, So here goes the n axis, and here you have x sub n. Okay, and just for convenience, let's consider 1 over n. Got it? Suppose you want to show that 1 over n is close to 0 for sufficiently large n. What does that mean? You choose some epsilon positive, say 10 to the negative 5. Okay, and given that, what? You must be able to find n over epsilon. Here, you find n over epsilon as 10 to the 5. Okay, then what happens? At 10 to the 5, you have xn minus 0 actually equals 10 to the negative 5, right? So for all integers. And then what does this mean? If n is greater than or equal to n over epsilon. So here, this is n of 10 to the negative 5, your choice. It's not unique, but you have chosen n of epsilon as 10 to the 5 here. And you now see the power of equality here. It's much easier. Otherwise, you need some other number, but anyway. So you draw a line. And what happens? In this region, when n is greater than or equal to capital N of 10 to the minus 5, what? For every n, your difference, your error, is less than epsilon, 10 to the negative 5. Got it? And also, you could change epsilon much smaller, 10 to the 10 million. Again, your n of epsilon can be chosen as 10 to the 10 million. And after that, every error is smaller than epsilon, right? So this is the definition of convergence of a sequence of real numbers. Now, caution, if you put equality here, as I told you, this is totally wrong, because if you choose epsilon equals 0, what happens? And also, suppose xn equals y, okay? Then 0 less than 0, totally wrong, right? Or here, suppose we have xn equals 1 over n. In that case, x sub n is never equal to 0. So this can never equal to 0. But if you choose epsilon 0, this is totally wrong, right? Even though xn converges to 0. So here, what I want to emphasize is that never put equality here. Got it? And here, it doesn't matter in most of the cases. So this is the one of the approach to show x is close to y. You construct the sequence x sub n and show that it converges to y. Got it? The problem of this approach, the second approach, is this. You can show and prove it converges. So theoretically, for sufficiently large n, your approximation is justified. However, the convergence may be very, 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 very slow, right? And if the convergence is very, 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 very slow, then in an engineering problem, you don't know how much n you need to take, right? So not only the proof of convergence is important, but also in many cases, finding the convergence rate. So in this case, it converges 1 over n, something like that, right? That statement is also important. However, that part is usually very difficult. So what we do as an engineering student, and even scientists and even some mathematicians heavily relying on computation, they just use computers. So they program some code, they code some program and then show the graph. Okay, I have taken some number, and the simulation shows, or the computation shows that the error is small enough in practical sense, something like that. Got it? So never forget, bounding is very important. And it's a kind of diverging from the main topic, but I believe our nation something's wrong in our math education, because this bounding is very, very important. Actually, bounding is kind of almost in the center of mathematics for a long time. Consider the example. You want to find what is number pi. You can easily define that as a ratio of the circumference to the diameter of any circle, right? However, people had some misunderstanding or wrong approximation. As I told you, the old statement says that in one line, pi is 3, okay? It really says pi equals 3. However, the Greek mathematicians knew that it was not 3, impossible, something like that. And what they wanted to do was what? Approximating pi using the regular polygon. It may enclose the circle, or it may be enclosed by a circle. And using two regular polygons, they could find the upper and lower bound on the value of pi. And the problem was that that geometrical approach had very slowly converging upper and lower bounds. So practically, they could not get more than the 10th position of decimal expression, something like that. And there was a huge breakthrough by, Isaac Newton, who invented the calculus. And he used his tool, calculus, actually, to find a very fast converging sequence of numbers to pi, something like that. And it was amazing. And after that, after the kind of Newton's invention or Newton's new approach, there followed many, many, many approaches, much better approaches, using sequences of real numbers to upper and lower bound the value of pi, or find a kind of approximate value of pi, something like that. Okay? And that history is totally gone and it never taught, unfortunately. However, it's very important. And one of the books I really love is this one. You may hate my diverging too much, but let me talk about the book. It's the history of pi, okay? And if you type history of pi, you will see some novel, pizza, pi. Okay. Yeah. And the author is Beckman. Let me see, history of pi, Amazon. Okay. Yeah, 1976, very old one. Yeah, this one. History of pi. Okay. And this author, Beckman, was not a mathematician. He was a professor in electrical engineering. And he was a defector from, I believe, Czechoslovakia when it was communized after the World War II. Anyway, he was a defector. And I don't know whether he lived a happy life or not. But interestingly, this book not only talks about the history of pi, in very detail, he also criticizes communism a lot. And actually, it influenced me when I was young and I was reading the book, okay? And kind of, you enjoy history of pi and also hate communism, something like that. And I brainwashed. Anyway, this book is also translated in Korean, and you can find it from our library. And also, the author updated his appendix, where he put the most recent, at that time, numerical computation of pi up to some millionth point in decimal representation, something like that. Anyway. And also, there followed some other books, and most of them are also translated. One of the book is Imaginary Tale, which I really love. It's not the tale of dog's tale. The imaginary tale is about the story of square root of -1. And The book is also written by a professor in electrical engineering in the US, I remember. And this book really nicely written and derives the Kepler's 3 laws of planetary motion, just using, of course, on a 2-dimension, using the Newton's the gravitational force equation and using the e to the j theta equals cosine theta plus j psi theta, the Euler's identity. Very, very nice and amazing. I really love that. Okay? I have this copy. And there is another one, but I will stop here. But anyway, so unfortunately, I've never seen, when I was serving as in the admissions committee, I never seen some high schooler saying that the most impressive book was History of Pi or Imaginary Tale, unfortunately. Anyway, so preview. Topics related with autocorrelation functions. As I told you, I'm going back to chapter 9.1 of the populist and then back to chapter 7. So here goes the one of the figure I didn't provide to you. So this figure, and you may say that no, you already told me. Actually, it is not. So let's recall some definitions. So definition 1, a random process is stationary to order 2. If, what was the definition? Stationary to order 2. So you talk about the irrelevance of the choice of the time origin in terms of what? Second order CDF, joint CDF. So joint CDF of x of t1 and x of t2. They are 2 random variables, right? Given a random process. And you have 2 arguments. And they are what? They are translation invariant, which means that if you shift the origin by delta or negative delta, it doesn't matter. These 2 functions, see that? This is a 2-dimensional function, right? This function is same as this function for all x1 and x2, and also for all t1 and t2, and for all delta. Ready? And then they are, the x of t is stationary to order 2. And here, when I talk about the meaning of this function equality, in 2-dimensional planes. First one was on T1 and T2 versus T1 plane. And the second one was X2 versus X1 plane. And what does this mean? So you choose some T1 prime and T2 prime. And then you can move that point by adding same value delta. What does that mean? You move along a line that crosses the point T1 prime comma T2 prime and having slope 1, right? So for T2 versus T1 on T2 versus T1 plane, on this line, you can choose any pair of T1 and T2, and at any point, the joint PDF of XT1 and XT2 is the same, right? So on this line, you have a single invariant second order joint CDF. And if you choose another line with same slope 1, you have another but invariant joint CDF on this line, something like that. In that sense, this figure looks like that one, right? I draw a lot of parallel lines to the straight line T2 equals T1. However, and also here, you may plot the contours of the two-dimensional PDF, and you may say that, okay, I have, for example, the circular Gaussian density, something like that, for this line, and for that line, you have some non-circular, non-zero mean Gaussian density for different line, but they do not change if T1, T2 moves on this line, something like that. Okay. Now, the figure is slightly different, and we are talking about the autocorrelation function over Y-sense stationary random process. Okay, or autocovariance function over covariance stationary random process. What does that mean? The covariance function, normally defined as a function from R to the 2 into R when X is real valued process, is what? Has strange property. If you draw a straight line with slope 1, on this line, what does that mean? The function value does not change. So in general, your autocorrelation function is a two-variable function. So if you have T1 and T2, you have some strange function. We don't know. It depends on the autocorrelation. However, you may say that on this T1 and T2, the value can vary, right? And why? Just to consider a very extreme random process. X of t is deterministically equal to cosine 2 pi fct. Then what happens? That is also a random process, even though there is no uncertainty. And what does this mean? On this line, you have, in that deterministic case, you have x of t1 squared. And if you scale cosine, it's a function of t. So if you move on this line, what happens? Here, the value is 1. And if you move, it goes down and touches 0 and goes up, touches 1, goes down, right? So in general, along the line, it is not necessary for us to have a constant, right? For a general random process. Even on this line, you don't have constant. However, if you have, for example, Y-sense stationarity, then what happens? There exists some function, R sub xx. They have the same name, but there are many Honggil-dongs in Korean. So you can have one-dimensional function, Rxx, that is a function of the time difference. In that case, what happens? What does this mean? If you fix T1 minus T2 equals, for example, 0, then you move along this axis. Then what happens? Your value must be a constant. So Y-sense stationarity means that general two-dimensional function, the autocorrelation function, has some interesting property along the line parallel to T1 equals T2. It's constant. So on this line is some constant, and you know the value. What is that? That is Rx of 0. And you move toward right side, then what happens? Here, Rxx, let's say this is 1, for example, then you have the value R sub xx of 1 here, because T1 minus T2 equals 1 here, right? And for example, suppose this value is 2, and on this line, what do you have? The function value that could be positive or negative if it is real, that is Rx of negative 2, something like that. So in that sense, your autocorrelation function, if you just examine the autocorrelation function and the mean path, and suppose mean path is constant. And second, you examine the autocorrelation function drawn on a two-dimensional domain. And it has some property like that, right? Then you can, by inspection, you can see that it's a wise and stationary random process. And you may say that, what's the use of it? Actually, it's very useful when you do digital signal processing. For example, you observe a random process and you don't know whether it's wise and stationary or not. But anyway, you take a lot of samples. And then you assume, of course, ergodicity and chunk them with overlapping or non-overlapping segments and take the mean. And it seems it's very close to constant. Okay, so you assume that, okay, mean looks like constant. So let me assume it's constant. And then you somehow calculate the estimate of the autocorrelation function. And to do that, what you do usually is that you take the chunk, then it becomes a vector, and you multiply this vector with its transpose. And you have a rank 1 matrix, but you time average that more than the size, the one size, the length of the vector. And it could show you some matrix that looks like Toeplitz matrix. Symmetrical and Toeplitz matrix means that it's not only symmetrical, but also what? Its main diagonal having the same value, and it's off diagonal by 1 and -1 having the same value, 2 off, second off. So you can then guess that what? Okay, it seems this process is wise and stationary. So this approach is very useful. Okay. Last night, actually, I took my old digital signal processing textbook used in my graduate time, and so it's almost 23 years ago. And I have found that it's very unfortunate that we don't now offer the digital signal processing courses in our undergraduate program and also graduate program. So I was determined to offer that at least next year. So if you still live around here, you'd better take that digital signal processing. Okay, anyway, so this is what I wanted to show first. And you may say that I knew already. Okay, it's okay. And now, this appeared actually in the qualifying exam this year. And the question was, what is the definition of positive definiteness of a matrix A, square matrix A? And unfortunately, among 27 students, only 1 or 2, only a few students got the exact answer. So I was very surprised. Anyway, so given a real n by n matrix, A is positive definite. So this is definition and this is notation. If what? X transpose AX equals is greater than 0 for all X non-zero. Okay. Or you may say that X transpose X is always greater than or equal to 0, and with equality holds if and only if X equals 0, something like that. But many students, made a mistake. Some 1 or 2 mistakes. Anyway, this is the definition of positive definiteness, and here goes the definition of positive semi-definiteness. Here we have positive semi-definite function. Okay, this is positive definite matrix. So here goes the definition. A real valued n by n matrix is positive semi-definite if X transpose AX is greater than or equal to X for all X. Got it? So that is the definition of positive semi-definiteness of a square matrix. A is not necessarily B symmetrical. Anyway, so the lemma says that correlation function as a 2-dimensional function or covariance function as a 2-dimensional function. So we do not assume wise and stationarity or something. But here, let me see. Oh, actually, it assumes x can be complex valued. So let me little bit change then. So let me modify this to complex. And here must be transposition. Yeah. And here, complex, Hermitian transposition, and complex. Got it? Yeah. So in this lemma, we assume x can be complex valued. So our autocorrelation function is defined as what? X of t1 times x conjugate of t2, right? And for the covariance function, we subtract the mean. And that is not necessarily constant anyway. And autocorrelation function is a positive semi-definite function of t1 and t2. What is that? First, the definition is this one. For all, so first you need to choose some n. For all n integer. And for all pair of ai and aj. Oh, okay, we have ti, tj. Okay. For all n and for all ai, aj, where ij is greater than or equal to 1 and less than or equal to n. So you choose some integer n. You choose some vector a of length n and some vector t of length n. Got it? So you choose n, you choose a and t. And what does that say? This is a definition, positive definiteness. What is it? You can rewrite like this. A Hermitian transpose times Rxx A is greater than or equal to 0, which means that actually here R sub xx has ij's component, that is the autocorrelation function evaluated at ti and tj. Okay. And when I first saw that, I thought the definition was incorrect because I saw some other definition like this using integral form. So you have some w of t, a function. And then somehow you mimic the quadratic form using functions. So w conjugate of t, autocorrelation at t comma s, and you multiply ws and double integrate over t and s. And if this is greater than or equal to 0 for all w of t, then the function, usually it is called kernel, is positive semi-definite. However, our definition in the populist textbook involved the finite number n. And actually, you can show that if we take w of t as a very special function that consists of finite number of Dirac delta functions, then actually this definition reduces that definition. And also you can show that for smooth enough function, the converse is also true. So just the practical way is accepting the populist definition. And also you remember, you can also extend it in this integral form. And here is the definition. And what is then proof? Proof is amazingly simple because if you use the definition, you can rewrite this summation like this using expectation. And what is that? This is a complex number and it's conjugate. So it must be greater than or equal to 0. So proof is too simple. And why the autocovariance function is also positive semi-definite function? Because autocovariance function is an autocorrelation function of the original function minus the mean path. So it's a autocovariance function is the autocorrelation function of some other random process. So it inherits the property. That's all. Okay. And next, we need this notion. And when I first saw someone who I admire in his research was using this definition, I was surprised that where he and wondered where he could find this definition. Did he invent it? I thought. And eventually, I found the definition from our populist text. It seems a populist probability and random processes book is a kind of Bible in this topic, as Gilbert Strong's the linear algebra book is also a kind of Bible in introductory linear algebra, and Proikis digital communication is a kind of Bible for every communication engineers. Anyway, here goes alpha dependent random process, and also M dependent random process, and alpha dependent a correlation alpha dependent random process, and correlation M dependent random process. So I want to just introduce you 4 definitions. And the definitions are actually very simple. First, alpha dependent random process is usually for a continuous time random process, this definition. And what does that mean? If you have 2 intervals in the time, and if they are separated more than alpha, the process, the random variables, every random variable in this interval and every random variable in this interval, they are independent. And you may say that it's too strong assumption, right? Too strong definition. However, without using, for example, this kind of very strong assumption, it is sometimes hopeless to derive anything useful. Okay? So it is very strong, and it may not be true in many cases. However, it may be approximately true. So in order to handle rigorously in mathematics, we need some definition like this. And also for discrete time random process, now here M is an integer. So you have a consecutive interval in discrete time axis, and you have another consecutive interval. And these intervals are separated more than M, some, for example, 5, 7. Then 7 dependent discrete time random process means that if the intervals are separated more than 7, then all the random variables are independent. Got it? Same as correlation alpha dependent and correlation M dependent. For the first definition, you calculate the correlation function of a random process. And if the time difference between T1 and T2 is greater than or equal to alpha, correlation is 0. Got it? So if you remember this T1, T2 plane to draw a correlation function, what does that mean? Here you have all 0 values, and here you have alpha. Got it? Only in this region, in this strip, you can have non-zero value if you have correlation alpha dependent random process. Same for the discrete time random processes. Got it? And for the white noise, I already told you last time. So white noise defined not in terms of power spectrum, but in terms of autocorrelation is more general. And there, the definition is very simple. White random process or white noise X means that you are, first, you have infinite power. And second, if you take 2 random variables, X of T1 and X of T2, they have a 0 correlation if T1 is not equal to T2. which means that your correlation function equals sum function of T1 and T2 times delta of T1 minus T2. So if T1 is not equal to T2, this is 0. If T1 equals T2, this reduces to sum Q of T1, delta of T1 minus T2, or equivalently Q of T2, delta of T1 minus T2. And you define this function. You introduce new single variable argument function and saying that white means random processes white means power is infinite and autocorrelation function is a function of T1 times delta of T1 minus T2. That's what I told you last time. Got it? So this is kind of non-trivial white noise. Probably in your undergraduate program, you've always seen something like my correlation function is a function only of tau, and you have some constant n naught over 2 and delta of tau, something like that. However, in general, this can be some other value, right? The problem is that here you cannot just replace this n naught over 2 as some function of tau. You can't do that, right? Because this expression requires you have T1 and T2, right? However, that definition rarely appears in engineering application, especially communications and signal processing, electrical engineering, because we usually need white noise to model thermal noise, which have almost a flat power spectral density. And we may assume that bandpass filtered version is wise and stationary. So this is for non-stationary white noise. Got it? General, stationary, or non-stationary white noise, we have this autocorrelation function. However, for wise and stationary random process, something like this is the autocorrelation function over white noise. Okay, last two topics, two definitions. First definition is a random process is mean square periodic. Second definition is the random process is cyclostationary. They appear very similar, and I found I have to talk about this before I continue to talk about the sequence of random variables. So first, let's remind us of the definition of a periodic deterministic signal. X of t is periodic with period capital T. What does that mean? X evaluated at t, some time instant t, and X evaluated at t plus capital T must be the same. And you continue that. That must be the same as the value evaluated at t plus 2t, of course, t minus 2t. What does that mean? Sometimes people equivalently write this as x of t equals x of t plus some nt for all t and for all n. Or they sometimes just say restrict t to some interval of t and draw a picture like this. Okay, you take this interval, and for example, this is the graph. Then how can you extend that? You copy that part and move to the right and move to the left by every t and paste. So you have something like this. Got it? So this is the definition of a deterministic periodic signal. Now, what would be the definition of periodicity of a random process? So this is also related to what I already told you. Here, see that the periodicity is defined by using the equality of two real numbers. What does that mean? Equality of two real numbers. That is equivalent to the difference of two real numbers is 0. So here goes the equivalent definition, right? So you have this definition, very familiar, slightly modified like this. Okay? And now you want to talk about a random process is periodic. So what do? What you do is that you replace lowercase x to capital X. So random process x of t minus process evaluated at t plus capital T is 0 in some sense, right? That would be your definition of a periodicity of a random process, right? And here, that's in some sense, for that in some sense, we use mean square sense. And you know what does that mean by mean square sense? Something's error, right? Squared and expected to 0. So what you do is that you take this idea and then define mean square periodicity in this way. See that? You take the absolute value, or if a complex modulus squared, and you take the expectation, and equals 0. Of course, here I forgot to use this must hold for all t, and this also must hold for all t. So this is the definition. So this is the definition of mean square periodicity of a random process with period t. And you know from this logic of order, this definition is not strange. But when I was at your age, the definition was very sudden and unreasonable. But I hope you find it very reasonable. And now, since we have defined the mean square periodicity of a random process, we want to have some consequences. We want to derive some lemmas. And here goes the first one. The first one is that x of t equals x of t plus capital T. Two random variables are equal, almost surely. You don't know that exactly now. So I may defer the discussion on this one. But rather, the second one is much easier. Of course, we have to use this one to show that the mean path is periodic. And suppose this is true. Now, you want to compute the mean path of the process. So what do? Expectation of random variable is always what? The value times the density. Integrate. So you integrate the value. You take entire value as 0. And you find the PDF of this entire thing, random thing. That is the first order PDF, right, of x. Now, the above one, which we haven't proved, means that what? Two random variables are almost surely equal, which means that two random variables may have the same first order PDF. So here you replace this second factor to f of x evaluated at t plus capital T. Now, what is that by definition? That is expectation of capital X of t plus t. And what is this? It's a mean path evaluated at t plus t. Means what? The mean path is a periodic function with period t. Got it? So mean square periodicity of a random process implies the periodicity of the mean path of the process. The third one, sorry. Yeah. You may say that. Here goes the third result is about, sorry, not this. Yeah. Third one is here. Third one is related to the autocorrelation function. And this is interesting. If x is mean square periodic with period capital T, its autocorrelation function as a function of two parameters is what? Is periodic in the two-dimensional plane. And you may say that, what do you mean by periodic in two-dimensional plane? Anyway, let's derive this one first. Okay. To derive this one, let me see. Okay. Still, this is not right place. Yeah, I already put. Okay, so let's prove this one first. And you've seen something similar to that, right? When we prove that the autocorrelation function, real valued random processes autocorrelation function or complex valued, this magnitude is upper bounded by the autocorrelation function evaluated at 0, if it is at least Weiss and stationary. And we do the almost the same thing. So consider two random variables. Actually, this is the same version as that one. And using the discriminant of the quadratic equation, we can show that Schwarz inequality holds. And here, the inner product is replaced by the expectation of the product. So in general, you remember Schwarz inequality is for the two vectors. But here, we extend or generalize it for two random variables by replacing the inner product as the correlation. So this is the kind of inner product of two vectors. And its squared is upper bounded by the norm square of the vector W and norm square of vector Z. Same thing, right? This is Schwarz inequality. And if you have confusion, just remember you have unit matching. So if W is in meters and Z in seconds, this must have meters squared and seconds squared, and you have meters squared, seconds squared. Got it? And now, in order to prove this is same as that one, what we do is this. We define W as x of t1 minus x of t1 plus capital T, and Z as x of t2. And don't ask why. And you will see why we do that to prove that. And then we plug W and Z defined like this here in Schwarz inequality. And now, first, what is expectation of WZ? So you multiply these two. And you know what? By definition, this expectation is simply autocorrelation evaluated at T1 and T2 minus autocorrelation evaluated at T1 plus capital T and T2. So left-hand side is nothing but this one is same as the difference between two autocorrelation function evaluated at T1, T2 and T1 plus capital T, T2. Now, what about the right-hand side? Let's focus on the first one. What is the expectation of W squared? And W is x of T1 minus x of T1 plus T. And we've already seen that from the mean square periodicity of the random process, these random variables are almost surely equal, which means that the difference is 0 almost surely. And you square it and expect it, you take the expectation, it's 0. So what do you have? Something squared is less than or equal to 0, and something squared is also greater than or equal to 0. What does that mean? By so-called sandwich lemma, it must be 0. And something squared is 0 means that something is 0. So you have autocorrelation. So this means when x is mean square periodic, your autocorrelation function evaluated at T1 and T2 equals your autocorrelation evaluated T1 plus T and T2. And now you do the same thing by changing T1 to T2 and T2 to T1, and you have something like this. Now you define this as T2 plus capital T or something like that, and eventually you have be careful. So for any pair of T1 and T2, and for any pair of M and N, of course they are a pair of integers, and these are pair of real numbers. Okay. And this is the result. So as we've seen in the above, T1 and T2, T1 plus MT, and T2 plus NT, and M and N is not necessarily the same. Now let's visualize this one, which I always love. And as you see from this figure, we can do something similar in the 2 dimension. So here you take the graph of this periodic signal on a finite interval, and then you copy it and paste it, right? By moving forward and backward integer multiple of capital T. Now, what does this mean? What does this mean? So what you do is that here you have T2 versus T1, right? And let's focus on this region where the horizontal length is capital T and vertical is also capital T. And you push Control C, okay? So here you have some function. If autocorrelation is real, you have some function, right? And what does this mean? The first one. You right shift this entire picture by capital T, you have the same thing. So here, if I draw correctly, you have something like that and something like that, everything, right? And now let's do the second thing. What does that mean? You copy this one upwards. But this holds for every color. Means that if we make an analogy, you go to Hyoja market and find some store that sells tile. You want to pave on your restaurant. You buy the same tile, right? You buy the same tile, 100 same tile, and pave your restaurant. Got it? Something like that. That is mean square periodicity's consequence in terms of autocorrelation. Got it? So suppose you have a mean square periodic random process. It's not likely, right? In reality, it's very unlikely that you observe mean square periodic something. However, when I was a graduate student, my friend in mechanical engineering, especially precision engineering, actually wrote a paper, PhD thesis, related to this one, because he was analyzing some milling machine or something, and he wanted to make a very circular cylinder. And you know how the machine works, right? You have some roughly circular cylinder and fix it to some axis. And you rotate that axis and you have some cutter, right? That cutter is very strong, and when your rough cylinder rotates, it cut off some uneven surface material, right? The problem is that if you have very small misalignment in axis, what do you have? You have non-perfect circle in the cylinder. And that is very important if you build a very, very high precision machine, like some cylinder that needs to put in a rocket, something like that. Small, very small error could lead to a digest, some boom, blow up of $1 trillion rocket, moon landing machine. Okay. And in that case, what happens? It must be a periodic random process. If you measure that using a laser, actually he measures using a laser. It's like there rotates the cylinder after the operation, and he just put the light source, laser, and measures some nanometer scale fluctuation. Of course, that measurement equipment has noise. So you have actually some periodic signal corrupted by noise. and he had to analyze that. In that case, definitely similar definition to mean square periodicity is necessary, right? But other than that, I don't know. But it is closely related to the next very important definition. And at the first glance, when I first saw it from the populist textbook, I thought, what? They are the same. Actually, they are not. Okay, that is the cyclostationarity or Y-sense cyclostationarity. So Y-sense cyclostationary, if mean path is periodic, it really looks the same, right? Second, autocorrelation function is what? Looks exactly the same, is it? No, actually. There is a difference. If you rewrite this one using some n or m, now you have same number, okay? Here, you moved by capital T in both argument. Means that if you move m times t in the first argument, you also must move in m times t, not arbitrarily n times t. This is the definition of cyclostationarity. This is definition. And let's plot the autocorrelation contour. And here goes the difference. Let's start from this square, our friendly, capital T, capital T. And you buy a tile. And what do? When you pave the surface, you move diagonally, right? So you buy this tile and only put them on this diagonal. And you buy another one, another set, different one in general, and put in the first off diagonal. If it is real, then probably you flip that one and pave the same way. But for the complex, it may have arbitrary function under some constraint. So do you see the difference? Then which one is more general? So which set is bigger? The set of mean square periodic random processes or the set of Y-sense cyclostationary random processes? Cyclostationarity is a bigger set because the previous one is a special case. This figure, where it is? Yeah, this one is a special case. Of course, you have on the main diagonal, same tile. And of course, on the first off diagonal, same tile, but their tiles are the same. So this is smaller, much stronger subset of Y-sense cyclostationarity. Got it? So mean square periodicity is a special case of Y-sense cyclostationarity. And even though I'm not talking in detail about the usefulness of this definition of Y-sense cyclostationarity, let me just tell you like this. Almost every man-made digitally modulated communication signal is cyclostationary. So in digital communications, we have a long history of some small faction, small group of people focusing on what could be useful if I model the man-made digital communication signal as a cyclostationary random process rather than Y-sense stationary process. Of course, Y-sense stationary process assumption, even though that is wrong, okay? Assumption does not generate two wrong results. However, in some applications, if you assume the digitally modulated signal is Y-sense stationary, then you make a mistake. And the difference between precise model and the rough model can be large enough to generate some very good research work. Got it? Anyway, so here, mean square periodic, then cyclostationary. So here, the set of all random processes, then here is Y-sense cyclostationary, and here mean square periodic. Got it? With here, by the way, we say cycle period T. here we have with period t. They serve almost the same role, but it's different because cycle period is not period. Period is a cycle period. Anyway, okay. Okay, we have only 4 minutes left, but let's go back to chapter 7 of Populist book. So in the review of last meeting, I've already talked about the importance of strict positivity of epsilon. When you use for every epsilon, blah, 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 magic spell in the definition of a convergence of a sequence or continuity of a function at some point or everywhere, something like that. Okay. So let me skip. Last time, I made a little bit of mistake here when I talk about the Cauchy sequence. So it's like this. The definition of a convergence of sequence of real numbers or complex numbers required your target limit. So you have a sequence and your limit, and then you show that for every epsilon positive, for sufficiently large n, your x sub n and your target, the difference is almost zero, right? So your definition requires the target, but sometimes you don't know what it is exactly. You can define it, but you don't know the number. So Cauchy somehow devised the way to classify a sequence. So here is, for example, a sequence of all real numbers. Got it? And here is convergent sequences. And he defined another set. And it turned out to be the same set. But interestingly, the set of Cauchy sequences, it does not require the target. And here goes the definition. For every epsilon positive, there exists the n, an integer number, such that for m and n greater than or equal to your choice of n, x sub m and x sub n, the difference is less than or equal to epsilon. And this is different from what you've already seen. At that time, your, for example, x sub n was 1 over n, right? And if you choose epsilon to 10 to the minus 5, you could choose n of epsilon as 10 to the 5. And then what could you claim? For every n greater than or equal to this n of epsilon, 10 to the 5, the difference between your limit and the element is less than epsilon, right? Now, this is different. You are almost the same up to this point, but what you do is this. What you do is this. So this is n, and this is n of epsilon, and you can find some upper and lower bound. And the difference is epsilon, and every xn prime and xn double prime here, your n prime and n double prime, the difference is less than epsilon. So even though you do not know the limit, from this point, you can find the so-called supremum of xn, or maximum, if you want, or minimum of xn for n greater, m and n greater than n. Okay, so minimum and maximum. The difference is the biggest, right? Among all. This is less than epsilon. Got it? So without target, you define some set attribute, saying that if that is true, Cauchy says that it's a Cauchy sequence. And interesting thing is that for the set of real numbers, and here our limit is also could be a real number. In that case, these two sets are the same. However, be careful. Suppose you have a sequence of rational numbers, and you only consider the limit in the set of rational number. Then, even though a sequence is Cauchy, it does not converge. For example, suppose you have square root of 2, and you know what it is. It's an irrational number, and it has 1.41 blah, blah, blah. And now what you do is that your first x1 is 1, sorry, 1.4, x2 equals 1.41, x3 equals 1. Something like that. So what you do is that you construct a sequence of rational numbers from the decimal expression of square root 2. And you know that all the elements are rational numbers. And this one definitely converges to irrational number, this one. So Cauchy have shown that if the space is not complete, that is complicated, but space is not complete, some Cauchy sequence may not converge in that space. So suppose we only play with rational numbers and we construct a sequence that is Cauchy. It may converge to some number outside that set, the irrational number root 2. Got it? However, as an engineer in 21st century, we use computers. And computers, in theory, have finite precision. So we can always handle rational numbers in some sense. Got it? After equivalent mapping. But in engineering world, we have irrational numbers too. Then do we have serious problem? Actually, no, because we always allow errors in our measurement, or our physics says that there could be, theoretically, there must be some error in measuring anything, right? So that's not a big problem. So for engineering sense, you may say that if a sequence is Cauchy, it's convergent in engineering sense, okay? So don't worry too much about using the definition of Cauchy sequence to prove the sequence converges. But be careful. Be careful. Sometimes students just take two consecutive terms and say that, okay, for every epsilon positive, I can find some n of epsilon. If mn n greater than this capital N, then it's very small. And they took consecutive numbers. And here goes some example. Suppose the sequence xn equals root n, which does not converge, right? And your high school math have asked you to show that the two consecutive numbers difference converges to 0. Is it really? It blows up, right? However, as you've seen, you multiply square root n plus 1 in the numerator and denominator. You can show that this number is same as that one. And if it tends to infinity, it goes to 0. So difference between two consecutive terms in this sequence goes to 0. However, it is not Cauchy at all. That's why it does not converge. Got it? So be careful. Okay, that's all for the day, and quiz will cover up to this point.